inference as a service for particle physics computing challenges. So here's a nice picture from our article on Fermilab News today. So I quite like it. So you can see the hardware, and this is the brain. This is the LHC. So I'll be talking on behalf of many collaborators from Fermilab, MIT, etc., and also some Microsoft researchers. So Heather gave a very good LHC 101 already, so I can skip a lot of those. So we're the best known for the Higgs discovery, and actually in order to study the Higgs boson with much better precision to extract more information for beyond standard model physics, we have to collect more data. So in round 2, we already collected 150 inverse femtobarns of data. And for round 3, we're going to collect more. And we need a high luminosity LHC data set, which will be 10 times bigger to collect these, to study these. So in order to deliver more data, the LHC has to squeeze a lot of protons in each beam crossing. So actually, we face this challenge, which is called pi-up. So you have multiple interactions per bunch crossing. So for round 2, we're running at, you have 20 to 50 interactions per bunch crossing. And for round 3, this goes up to like 50 to 80. And for high luminosity LHC, this goes up to 140 to 200. So as a result, in order to take data effectively, efficiently, we have to upgrade our detector. So Heather talked about calorimeter and also silicon trackers. So here, as an example, at the very center of the CMS detector, we have the pixel detector, which is a semiconductor tracker. So basically, it's a very high-speed resolution camera that takes snapshots of the collision. And here you can see the number of channels of our detector. So the previous one's 66 million channels. And for phase 1 upgrade, which was constructed at Fermilab, the number of channels doubles. And for phase 2, it's going to be 2 million. So it's really challenging to, reconstruct the particle tracks coming with this hit because there's a large amount of data. So the event complexity will go up because we have more complex detector, and also we have 10 times more data. So roughly now we can process one high luminosity LHC data set with, in 5 minutes per event. But you put all these things together, we need about 3.5 million cores to process all the data. So compared to today, it's going to go up by a factor of 10, which means it will take years for us to process data before we can publish any paper, which is not very realistic. So you would think maybe this problem will get solved by itself with the development in computing power. But unfortunately, we can keep adding transistors in a fixed area. So Maury's law still continues, as shown here. But Dennard scaling fails, which means we don't get faster computer just by adding more transistors anymore. So around 2005, people started implementing algorithms using multiple cores on CPUs. So CPU is not the only solution hardware-wise for computing. We can also have GPUs, FPGAs, and ASIC. So basically, it's a balance between flexibility and efficiency. So you have, when you need to write a new algorithm, there's more flexibility on CPUs, but it consumes more power, it's slower. And there's a recent trend in industry exploring these heterogeneous resources. So using coprocessors, basically you have a CPU with either FPGA or ASIC or GPU attached to it. So you can, when you have neural network inference, you can offload some of the tasks to FPGAs, for example, to speed up the multiplication, but still do the I/O and other task managing with your CPU. So here we want to explore whether we can take advantage of this development with the coprocessors to speed up our reconstruction. So basically, you need to find the most time-consuming piece of reconstruction problem. Here, of course, tracking and also clustering are both very time-consuming. And these are very intrinsically sequential algorithms. So in order to take advantage of, for example, GPU, so you pick up a piece of GPU, you have to rewrite these algorithms specifically for this hardware. Or you can take another approach, recast these problems as neural networks, and they are free in terms of your choices of hardware. So here you can use FPGAs, coprocessors, etc. But of course, this is a challenging task, and which I think some of the authors actually adhere for this tracking problem using neural networks. So, and we should keep working on this. So we're betting our money on option 2. So as Heather mentioned, there's very active applications of neural networks in particle physics. Here, I want to point out also the networks we use nowadays is actually really small compared to the industry ones. So the largest neural network in CMS now, which is the deep AK8 algorithm, it's still very tiny. It has 0.5 million parameters, and you can barely see this in this plot. So we expect, with more complex detector, we will have more complex neural network algorithms, and also the number of applications will increase. So those are the arguments for exploring this coprocessors as a solution for our computing problems. So here we, so this paper is in collaboration with Microsoft Brainwave research team using their FPGA coprocessors to answer a question of how we do this. To summarize our paper, we showed as a proof of concept we can do top tagging and neutrino image classification with their service. And also this service is implemented in CMS software framework in a non-destructive way. And also I'll show you the speed and data throughput performance. So here's the Brainwave. So they have two fabric of CPUs and FPGAs, and everything is interconnected. And here you can see a piece of their hardware, which is the building blocks here. So they provide a very mature full service instead of just one coprocessor. That's why we started working with them. And they support several models, ResNet-50, so most of these are image detection networks. So you can take this networks and you can retune the weights based on your problem and your data set and optimize for the specific problem you're trying to solve. So they are working on the software tool sets to provide more flexibility. That say if you have a new model, you can use these tools to implement on their service. So we used ResNet-50 to do top tagging. So just to remind you what's ResNet-50, although I think everyone here knows. Basically, you have the featureizer part which extracts the features of the images, and you have the classifier part. And actually, only the featureizer is run on FPGAs, and that's fixed architecture. But the classifier part, you can change and redefine your classifier for a specific problem you're trying to solve. So this is, they have a pre-trained ImageNet for 1,000 classes. And you can take this and redefine for our top tagging problem. So top quark decays into jets, and also we are trying to distinguish the top jet against the QCD, which are like UD or S-quark jets. So jet by itself in our detector is actually not image-like, but we can choose how we represent the constituents in a jet to convert them into images. So here we took a public top tagging reference data set, which is provided for people to compare their favorite neural network architecture and see which one performs the best. So we converted this data set into images by basically it's a density map of the PT of the constituents of the jet. And here you can see that top jet tend to has a wider radiation pattern, and QCD is more narrow. So it's actually a great image, and we duplicate this 3 times because we don't have enough information to make this RGB by using, let's say, charge of the jet constituents. So you can take this and teach ResNet-50 what's a top quark and what's a QCD. And here's the performance we achieved. So there are several, caveats here, or like points I need to point out. So first, this is signal efficiency versus background rejection. So this is for top quark, and this direction is better. And this blue curve is the floating point. So all these are trained on GPUs and evaluated on GPUs. But we're not interested in optimizing the blue curve, because once you go to a quantized version, by reducing the number of precisions of the weights you use, you lose performance. And we have to retrain this in order to restore the performance. So you can see that this is the best performed for the quantized version. And then, so these are actually running, with the emulation on your GPU of their quantized version implementation. But once you upload that service to run on real FPGAs, the performance actually degrades. So we had to like retune the model. Sorry. We had to retune the model, so the features you get from the emulation, the features you get from the FPGA, actually retrain the classifier as well to restore the performance. So this is kind of comparable to the best top tagging from that public data set. We also use this to classify neutrino images. So these are neutrino images from NOVA. You have the electron neutrino, muon neutrino, and tau neutrino. So this method can be applied for future Dune processing for neutrino images as well. But this is done with transfer learning, which means we don't retune the weights of the featureizer. So this service is implemented in SAM-SSW using this external module. So you send event data to their service of coprocessors and get the result back. So this, doesn't interrupt our current computing model. And the performance we got is about 10 milliseconds for running locally and 60 milliseconds. So if you consider, the travel latency and the speed of light limit, plus some network switching, the difference between these two makes sense. And this improvement is more, depends on which CPU implementation you compare to. It's 4 to 100 times faster than CPU-only implementation. And of course, we can have multiple jobs sending, sending tasks of inferencing 5,000 images to the same FPGA single service. It actually can do really well. So basically, you launch the jobs here and send them to this single FPGA. And here's the performance we got. So this is the number of simultaneous jobs requests we send out. And you can see that the average latency is pretty stable in terms of, over the number of requests you send. And here's showing the same information, but with a little bit more information about the distribution of the inference time per job. And everything seems to be scaling up pretty well. And then, of course, we want to study how many data we can process given 1 minute. So, and this is directly comparable to, let's say, GPUs, where you can run in batches and process more data as well. So what we found is that the data throughput is actually comparable for single FPGA service versus GPU running with many batches, as shown here. So this is kind of a little advertisement as well. The industry focus is on the latency more than 1 millisecond. But actually, for our hardware level trigger, we need really fast inference in order to implement these online in data taking. So we have a separate work on the HL4ML, high-level synthesis tool for machine learning. And we were able to achieve 100 nanosecond latency for a relatively small network. It's fully connected network. And we are trying to implement these in SAMS for next data taking. I think, yeah, that's all. Thank you.